Sarah, we're back. This time live from Mumbai, India. Okay? And I hear you have a test tomorrow. You got a test on not just the electron ways of writing elements, like the orbitals and the subshells, all that, like the noble gas configuration. Excuse me. But also now you got to know some periodic trends. So, based on an element's positioning in the periodic table, what do we know about it? What do we know about its size? What do we know about its electron affinity? What do we know about its electron negativity? What do we know about its ionization energies? Not to mention, what the heck are those anyway? So what I have done is I have taken the liberty of getting this up to speed, hopefully making this very, very simple, straightforward for you. Not too textbooky, which is my style. I don't like sounding like a textbook, because then, you know, if I sound like a textbook, you won't listen to me either. Probably like you don't read a textbook, because I don't know anybody who reads a textbook for fun, much less to get informed on what the heck's going on. So, because of that, I've taken the liberty of creating a very cracked version of a periodic table, but it's got the first few elements in it, and here it is. So there we go. Yeah, first 10 elements in there, just to give you a sense of what's going on. Okay, so we got a couple of ideas here that we need to discuss, in addition to, like I said, how to write the electron configuration of nitrogen or oxygen or fluorine or neon. Basically, this periodic table is set up on electrons because of how many valence electrons something has or how many total electrons something has. Okay, so electrons, even though they're way tinier than protons and neutrons, and they don't even live in the nucleus, they're still very, 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 excuse me, very important. India is like almost exactly 12 hours apart from you, so if it's like 6, 7 at night where you are, it's 6 or 7 in the morning where I am, so I'm putting in some early hours to do this video for you, because I know you got a test coming up, and if you're taking it, hopefully this helps. You can look at it tonight. So, check this out. We have a couple of topics we want to deal with. I'll write them right here. These are the 4 main ones I think you guys are concerned with: electronegativity, ionization energy, electron affinity, which, yeah, I know it sounds like electronegativity, I know, and it's easy to get them mixed up, so we'll cover those, and also atomic size. Okay, so I'll touch on this a little bit. Electronegativity is how, or to what degree does one atom attract electrons from other atoms. Okay. Ionization energy is the amount of energy required to forcibly make something an ion, which in most cases means to add or remove an electron from it. But in ionization energy's case, it's the amount of energy required to remove only, not add, but to remove an electron from an atom. Electron affinity is basically the amount of energy, it's almost the exact opposite of this. It's the amount of energy per mole required to put an electron back on to an atom. Okay? An affinity is like a likeness, like, oh yeah, I like you, come over here, I got an affinity for you. So to what degree does an atom have an affinity, a likeness, an attraction, a desire for electrons? And then atomic size is what it sounds like. How big is the atom? Now here's the thing. Atoms are mainly empty space, like 90-something%, maybe 99 point whatever is empty space, because you got the nucleus, okay, which is tiny. Then you got electrons, which are tinier, and then there's nothingness in there. So you might say, well, yeah, basically most of the mass is in the nucleus, and I agree with that, but not all the size is in the nucleus, because the size does depend on the electrons. So If here's a nucleus and then there's an electron right over here, this is not the size of the atom. From here to here is the radius of the atom. So you got to account out for all that bit blank space. So it's all dependent on electrons and protons. Here we go. So I'm going to start off with the size component. Okay? And let's take a look at oxygen and at fluorine. Okay? Oxygen has how many protons? Well, it depends on what its atomic number is. Okay? Or you just count from the upper left. 1, 2, 3, 4, 5, 6, 7, 8. Its atomic number is 8. Oxygen's is, it has normally, under normal circumstances, when it's not an isotope or an ion or anything like that, it's got 8 protons, 8 neutrons, 8 electrons, most likely. Okay? So for oxygen, we got 8 protons, we got 8 electrons. For fluorine, right next door, we got 9 of each. Okay? Now, if I just asked you, Sarah, what's bigger? Something with less junk in it or something with more junk in it? If I ask you what's bigger, you'd probably say more junk. The fluorine should be bigger. Okay? And that's logical to presume, hey, it's got more stuff and it's probably going to be bigger. Okay? No, fluorine is actually smaller. And at that point, that's why people sometimes say, the hell's going on? Why? That doesn't even make any bit of sense. I don't get it. That's craziness. But here's why. Think about it like this. We have charges going on. And where there are opposite charges, protons and electrons, positive versus negative, we got attraction. Okay? Now keep in mind, valence electrons are also very important. So when you have something like oxygen or fluorine, if you remember from last time, the outermost energy level is the second energy level for either of those. The outermost subshell is the 2p subshell. Now, because oxygen and fluorine are right next to each other, both of their outermost valence electrons live in the 2p subshell, energy level and subshell. So that being said, they're like in the same location. Okay? So that leads to them being at least the same size, because remember, here's the nucleus, then the first energy level is like a sphere around. You can think of these like little like balloons within balloons, or maybe like the ripples when you drop a stone into a pond or something like that. First energy level, second energy level. Okay? Yeah, there's more electrons and more protons in the nucleus, but those kind of have their own defined sizes. So fitting 8 versus 9 protons into the nucleus, yeah, it might make the nucleus bigger, but remember, it's at the center of the atom anyway, and there's a lot of empty space. So the nucleus could grow and grow and grow and grow, but it's not going to change the size of the atom, because that's really dependent on how far out the electrons are. And if all the electrons are in the 2p orbital, well, here's a nucleus, then here's a first energy level, here's a second energy level. If all the electrons are like still here, they're really, really small, so they're all going to fit, kind of like they're watching a TV show. They're going to be like all like pressed up against some glass window looking, okay, at the nucleus. So they're going to be the same distance away. But when there's more protons in the nucleus, there's more attraction, okay? There's more attraction for the electrons, because positives attract negatives, negatives attract positives. So they're going to want to be really super pressed up against that glass, if you want to use that analogy. So whenever there's more protons in a nucleus, even though there's more stuff there, that also means there's more attraction. So these electrons are going to be grouped together and maybe brought closer ever so slightly versus 8 protons. That's why fluorine, something to the right, is a little bit tiny little bit smaller than something to the left. And for that reason, oxygen is a little bit smaller than nitrogen. Nitrogen's a little bit smaller than carbon, which is a little bit smaller than so basically on the left you got bigger stuff, and on the right you got smaller stuff. More protons means more attracting of the electrons, which means a tightening up a little bit, and you can see that's going to be a little bit smaller than that. Okay? So going across a period or going across a row of the periodic table, stuff gets smaller. No, unfortunately, you don't just go left and right, you go up and down too. And that's more intuitive, okay? When you go down, you got, yeah, more stuff in the atom also, but the energy levels now increase. We go from energy level 1 to energy level 2 to 3 to 4, and those are, like further and further and further away, okay? So yeah, the electrons, as you go down the periodic table, the electrons are further and further away, even though, yes, there's more attraction, but they're still like locked in at fixed distances that are way bigger than like oxygen and fluorine. So therefore, as you move down a periodic table, you get bigger, okay? So if you get bigger, you being any atom, or the trends of atoms, as atoms get bigger going left and going also down for those various reasons, then it should stand to reason that atomic size gets smaller going either up or right or both. So if you ever see in your textbook or in your notes, hey, these little periodic trend arrows, you'll see atomic size going up to the right, okay, for getting smaller, or down to the left for getting bigger. Now, a common question would be, I think barium lives down here, period 7, second column, I believe. Okay, it's right next to francium or cesium or one of those. I would say, what is bigger, this or fluorine? I'd say, well, bigger is this, smaller is that. And you could either think, oh, because the arrow goes this way, getting smaller. That's one way, but you want to be able to reason. Okay, there are more energy levels further away from the nucleus. Okay, that's why something down here is bigger than something up here. Or heck, even something down here is bigger than something up here. Okay, it's all based on those energy levels are far away from the nucleus as you move down the periodic table, and they're closer to the nucleus as you get closer to the top of the periodic table. Now, there's this other phenomenon known as electron shielding, which I like to say, pretend you're at like a music festival, not so much in a stadium where you got seating that goes up like this, but let's just say you're like on a lawn somewhere watching a show and the band's on the stage playing and you're front row. Your view isn't really shielded from the band, okay? So if you like the band especially, you're going to want to stay there, hang out, watch the show. It's going to take a lot of work for somebody to get you the heck out of there. Okay, you're not going to want to leave your front row seat to the show. Your second row, that's still pretty darn good. Your view might be shielded a little bit by people in the first row, but it's not that bad. But then as you move further and further and further and further and further and further and further back, you might have more and more and more and more and more and more and more people in your way, so your view doesn't get quite as good. You might not be as interested in seeing the show because you're like, man, I can't even see a damn thing. Why would I be here? And then if you're back row, you may be like, dude, I can't even see anything. There's all these people in my way. There's no like hill. It's just like a flat surface. So, you're a lot more likely to leave, okay, or stray away. Get further from the band. You see where I'm going with this? So electron shielding acts in much the same way. The band that's playing is the nucleus, okay? And then you have electrons. The closest electrons, the ones in the first and the second rows, this first and second energy levels, like of the rows of the concert, those guys got the best view of the nucleus, okay? They're not gonna want to necessarily leave because they got a good view of the show that's going on. And the real reason in the chemistry is because they're close enough to the nucleus. Remember, you already took physics, so you remember Coulomb's law, where distance is inversely proportional to the electric force. The closer you are, the stronger the force is. So when distance drops, force rises. That's inversely proportional. Same thing here. The closer electrons are to the nucleus, the more they're attracted to the nucleus. Okay? Yet as you move away from the nucleus, you get in those higher energy levels, like the 4th, the 5th, the 6th, the 7th energy levels. Then all those electrons out there are shielded from the attractive energy of the nucleus by those electrons that are closer. It's almost like, think of a fire also. You could think of like, a bonfire. If you're really close to the bonfire, you'll feel a lot of that heat. But if you're far away from that bonfire, you're not going to feel as much heat. And the problem with electrons is, if they don't feel a lot of that heat or that attraction, they're going to stray even further away. So you get bigger. in terms of atomic size. Because if you move even further away from the nucleus because you're attracted to it less, your size increases. So that's what electron shielding is, and that plays an important part in really a lot of this stuff. So, atomic size increases going down or left or both. Atomic size decreases going up or right or both. Now, that takes care of atomic size. I've already messed up some of these, but we'll get rid of atomic size. Now, electronegativity. How much are electrons attracted to the atoms of other molecules? Okay? Well, it's for the same reason. If there's a lot of shielding going on, they're not going to be very, very attracted. And if there is not a lot of shielding going on, then they will be attracted. Okay? Because remember, a nucleus doesn't necessarily just attract its own electrons. It can attract somebody else's electrons if somebody else is close by. So, up here, where there is more attractive force to its own electrons, there will be more attractive force to other electrons as well. Therefore, electronegativity is very, very high here and very, very low here. So, for the same reason, here's what gets kind of weird. Remember, atomic size decreases this way because of the valence electrons, how far they are from the nucleus, electron shielding, how many protons are in the nucleus, all that good stuff. Okay? Atomic size decreases going up to the right. But for that same exact reason, electronegativity increases going up to the right and decreases going down to the left. So it's very easy for people, and when I say people, I mean I remember when I was learning this stuff, I got this stuff confused a lot. Okay? So you want to be clear. Because of shielding, because of electrons' locations, because of how many protons are in the nucleus, because of how much shielding there is, all that stuff, there is more attractive energy in the upper right of the periodic table. Therefore, size decreases, but because the size is dependent on where the electrons and how much they're being attracted, which is what electronegativity is, electronegativity increases up here and decreases down here. Okay? So keep that in mind as well. Next. This did say ionization energy. Okay. Now, an ionization energy is a physical amount of energy in joules or kilojoules that it takes to remove, not just make something in an ion, but remember there's two options. You either add an electron or remove an electron. Ionization energy is how much energy is required to remove an electron. And here's the thing. You can remove sometimes more than one electron. So you're going to have different ionization energies. But keep in mind the octet rule. Now you should have heard about this at some point. Octet, like octagon, means rule of 8. And most atoms follow this octet rule, which basically says in your outermost energy level, you would like to have 8 electrons. 8 is perfect, 8's stable, 8's happy. Okay? So, for example, oxygen again. It has a total of 8 electrons. Cool. But not 8 in its outermost energy level, it's just got 8 total. Remember, 2 electrons go in the first energy level, and then there's 6, 1, 2, 3, 4, 5, 6, in the valence energy level, which in this case is the second one. So, it would like to have 8 in its outermost energy level, 8 electrons. Right now it's only got 6. So it has two options. It can either get rid of the 6 it has already, or it could gain 2 more. Now similarly, fluorine has a total of 9 electrons, but 7 of those are valence because 2 are close to the nucleus, and then 1, 2, 3, 4, 5, 6, 7 are a little bit further away in the second energy level. So it has an option, actually 2 options. It can either gain 1 electron to make 8 in its outermost energy level and then become an ion, or it can lose all 7 that it has. And most likely it's going to want to gain 1 because that's a lot easier than losing 7. Okay, but something over here, like that used to be lithium, I'll rewrite that. See, something like lithium only has 3 total electrons. It's the third element. Now, 2 of those are in the first energy level, and only 1 is in the second energy level. Now it's got another option. It can either lose the 1 that it has or gain 7 more. Now, contrast that with fluorine. It could gain 1 or lose 7 electrons to be happy. My word is happy, meaning it has a full octet rule in its valence shell. This guy could lose 1 or gain 7. Gain 1, lose 7 electrons. Lose 1 or gain 7 electrons. Now, keep in mind that ionization energy is the energy required to remove an electron. Which do you think would have a higher ionization energy? Lithium or fluorine? You can pause the video to try to think about it. I'll tell you in 5 video seconds, okay? Higher first ionization energy is going to be fluorine, okay? Here's why. And notice I said the word first ionization energy, and that just means that if you have at least 2 electrons, you can have a first ionization energy and a second ionization energy. The energy required to remove the first electron, energy required to remove the second electron, or the third or the fourth. You can have an 80th ionization energy, technically, if you're a massive enough element down here in the bottom of the periodic table. Even 180th, to be honest. So, because lithium it would be a lot easier for it to just lose 1 electron than gain 7. It's not going to need a lot of energy to do that. It's what it's wanting to do anyway. So its first ionization energy will be relatively small because that's what it is looking to do anyway. Hey, it's like, hey, I got 1 electron in my outermost energy level. I could fill myself up with 7 more, or I could just give this 1 away basically for free. Anybody want it? And because it's having the mindset of, hey, anybody want this? It's not going to take like that sweet of a deal to make it happen. It's just going to say, hey, look, here, take it. So its first ionization energy for something like lithium on the left of the periodic table is extremely low. Whereas something like this, which only needs 1 more electron to have a complete octet in its valence outermost energy level, if it is only looking to gain 1, it's not going to want to give 1 away. It's going to have to take a real lot of energy, or like a really sweet deal, for this guy to give up an electron. So therefore, that's why this guy, or anything to the right, is going to have a higher first ionization energy amount than something on the left. So ionization energy increases going to the right. Now, like I said, there could be a second or third or fourth ionization. Let's say lithium loses its 1. Okay, now it's only got 2 electrons, but hey, that closest energy level only needs 2 electrons. So lithium's perfectly happy now. You think it's going to want to give up a second electron? I didn't think so either. And it doesn't. So therefore, it's going to say, hey, look, I have 2 electrons, but that closest energy level only needs 2 electrons. It's full. If you want to remove another electron, hey, that first one, I was giving it away. But now if you want a second electron, that's going to cost you. And it's going to mean that there's a lot more energy required to physically, forcibly remove it away from lithium. So something here would have a very low first ionization energy, but a very high second ionization energy, and a little bit less of a third ionization energy. Okay? Something like beryllium. It's going to have a pretty low first ionization energy, because remember, it's got 2 electrons in its outermost energy level now. So it could either gain 6 or lose the 2. But if we're going 1 by 1, it's going to say, all right, the first one, if you want to take the first one, all right, because then the second one I really want to get rid of. So its first ionization energy, it's not going to be that high, but it's going to be higher than its second ionization energy. This guy, once it gets to the second one it wants to lose, and then it'll have the full energy level beneath that, that's how it's going to get the lowest. Now, something like fluorine, remember, it wants to gain 1 or lose 7. So if it's going to start losing electrons, it's going to be really tough to remove those first ones. But once it's got like only 1 more to go, then it's going to be the lowest. So something like this is going to have a highest first ionization energy, but the lowest 7th ionization energy. Okay, because remember, right now it's got 7 electrons in its outermost second energy level, right here. So once you start knocking them down, it's gonna say like, hey, all right, I guess I'm losing electrons. Then the last one I need to lose is gonna be the easiest one. So that's the idea. Now, also going down a periodic table, do you think it would be easier or harder to remove electrons from atoms where there's a lot of electron shielding going on? See, I thought so too. And you're right. It would be a lot easier to remove electrons that are further away from the nucleus just because there's less attractive energy to begin with, like from Coulomb's law, and there's a lot of electron shielding going on. So electronegativities decrease this way and decrease this way. So going left and going down, electronegativities decrease, but going up to the right, there's that way again, up to the right, electronegativities increase. So you want to keep that in mind. So far for those 3 items, we have atomic size decreases going up to the right. Ionization energy increases going up to the right, and electronegativities increase going up to the right, all for the same exact reasons. Electron shielding, number of protons, distance from the nucleus, all that, okay? And finally, electron affinity is the basically energy required to put an electron back in, or how much energy is done to, or is needed when you have now a desire for electrons, not to remove an electron like electronegativity, ionization energy, but to have an electron put back. So all you need to know is that however much energy was required to remove an electron for ionization energy, and for this they basically compare it to that first ionization energy. So you don't have to worry about, well, what about the third or the fourth? Don't worry about that, just like the base case. So however much energy was required to remove 1 electron would be the same amount of energy that's required to put one back, but just in the negative direction, okay? So if ionization energy deals with an endothermic process, because you're putting energy into the atom to remove an electron, then putting an electron back is exothermic, okay? You're removing that energy that was originally there or originally needed. Okay, so keep that in mind. Ionization energies, and like basically removing an atom, removing an electron from an atom, endothermic. Placing an electron back, exothermic. Okay, so whatever amount of energy was required to remove an electron, that would be a positive amount, endothermic for ionization energies. It would be equal and opposite to put it back for electron affinity. So that would be exothermic, and the numbers would be negative. Okay, so keep that in mind. That's what we got. That's what we got for those 4 things, okay? Those 4 periodic trends. So if you have any questions, please let me know. Please let me know. And if you are taking this test tomorrow, November 3rd, and you have any questions, text me, and good luck. And if you're not taking it, let me know that too. And any questions about what I just rambled on about, as always, let me know. See you again with video number 9. We'll go back to math.